This is Knowledge Engineering with Semantic Web Technologies, Lecture 4 on OWL rules and reasoning. And today we want to talk about OWL complex classes because we have already learned about the basic concepts of the OWL web ontology language and now want to apply it to define more complex classes. So let's start with the first special case, the so-called closed classes. So these are classes in which the class members are explicitly enumerated in the definition or for the definition of the class. So look at the following example here. So we say novel is a class and Animal Farm is a novel, and also 1984 is a novel. And now I could define a new class which could be novels in store, which is a class, and then I define them novels in store in the form that I really enumerate all individuals which belong to that class. And these are Animal Farm and 1984. And to do this, I use a new OWL vocabulary word, which is OWL one-off. So if I define novels in store as an OWL class, I can furthermore say novels in store is OWL one-off, and then I define in braces simply all individuals which might be in that class. And this is then Animal Farm or 1984, which means there are only two novels available in the store right now. And you see also the equivalent definition in description logics in light gray right beside the box. So this is the possibility to define so-called OWL closed classes or nominals. Okay. Then, of course, we have the possibility to define more complex classes with the help of class constructors. And we know these already from description logics. These are first the conjunction, which is based or which is expressed with the OWL keyword OWL intersection of. Then we have the disjunction, which is expressed with the keyword OWL union of. And we have the logical negation, which is expressed with the keyword OWL complement of. So, as you know, logical constructors are usually applied to create complex class descriptions from atomic class expressions. And we will have some examples where exactly these class constructors are applied. So let's start first one with the conjunction. Let's first have a look at the description logic definitions. Here we see that book in stores are the conjunction or the intersection, you can say, among things in store and books. So these are then the books in store. How do I define this in OWL? Pretty easy. So first I define a class book, and then I define a class things in store. And then if I want to define books in store as a class, I can say this is the intersection of things in store and book. And I do this via a new OWL keyword, which is here called OWL intersection of. And then in braces, I simply enumerate what I want to intersect or what I want to conjunctively combine, and this here is things in store and book. And this means the class books in store results from the intersection of all individuals of the classes things in store and books. So this is quite easy. So OWL intersection of. In the same way, I can also define logical disjunctions. So with the help of the keyword OWL union of. And this here is another kind of class definition. Here I use explicit class equivalency. So if you look here at the description logics, again, I define book is equivalent to novel, disjunctively combined with poetry, disjunctively combined with non-fiction, which means book is novel or poetry or non-fiction. So let's define this here exactly, or the one-to-one translation into OWL. First we define book to be a class, and then we say, okay, this class book is equivalent to a complex expression. So I say OWL equivalent class, and then in a blank note definition here in square braces, I put my complex class definition. And this consists of first the blank note, which is combined with OWL union of. This is the disjunctive combination. And then in braces again the enumeration of all the classes which are here combined disjunctively, which are novel, poetry, and non-fiction. So you see here, this is a little bit more complicated than the last expression because here I use explicitly this OWL equivalent class. But don't worry, both kind of expressions are somehow equivalent, sure. So, next thing what we do, we want to use the complement expression. So here, for example, I say that books are a subclass of non-writers. Yes, it's pretty easily defined. So I define a class book, and as I say that this is an RDFS subclass of, and then for defining the complement again behind a subclass expression, this is the object, and in the object I first define a blank node, which is defining to be the complement of the class writer. So the blank node starts with here square braces, and then I say this one is OWL complement of, and then as object I define the writer. So what does that mean, that books are a subclass of non-writers? This means that books, of course, are definitely not writers, and that both of these classes won't have any individual in common, any member in common. So this expression, of course, is semantically equivalent to the expression that book is an OWL class and this is disjoint with the class writer. So you see there are equivalent assertions that can be made here with the help of that complement of expression or disjoint with when I combine classes with each other. So this is not necessarily, let's say, or this gives us no higher semantic expressivity, so this is only a similar or an equivalent expression. Okay, furthermore, let's have a look at so-called OWL property restrictions. Property restrictions are used to describe complex classes via the restriction of properties. And what I can do here is I can, for example, on properties, restrict somehow the range of a property and fix it to a class, and I can do this in a loose way or in a strict way. You remember loose binding or fixed binding, which means existential or universal quantification. This is achieved by OWL all values from and all some values from, and in addition to that I can also define a class by fixing the range or the value of a property to a specific individual or to a specific data value. And this I can do with OWL has value. We will shortly have a look on that, how this will work in an example. So these are restrictions on values. And then I can also define restrictions on the cardinality. So these are these number restrictions that we have already talked about. And number restrictions on the cardinality, for example, is this when I define what is a string quartet and I restrict the members of a string quartet to be exactly 4. I do this with the keyword OWL cardinality. And if I only want to define, let's say, upper or lower bounds, I can use OWL min cardinality for lower bounds, and I can use OWL max cardinality for upper bounds. But let's have a look at some examples. So first one, I have property restrictions with constants. So this is here the property on a specific individual. For example, here I can define, so first let's have a look at again the description logic expression. What I do here, I define a class which is called Orwell's books. And I say that Orwell's books is a subclass of everything which has been authored by one individual George Orwell. And if I designate or want to define an individual here and restrict the property not the range to a class, but to be the range a specific individual, then I use these braces. When I want to put a class there, I don't use the braces. So this is the distinction for description logics. Okay, but now let's have a look at the OWL definition. So here I also again define Orwell's books as an OWL class, and this is a subclass of. Again, I have to define a blank node, so I have these square braces. And then in this blank node, I put an OWL restriction on that. So, and the restriction always has two parts. The restriction must be applied here on a property, and this is the property author. And then I say of which quality this restriction is, and this I do with the OWL keyword has value if I want to restrict to a constant. And here I say this must have the value George Orwell. So I restrict the class that I define here, that on the property author it always has, or it only is allowed to have the value George Orwell. The class Orwell's books is here described via fixed value assignment, which is a constant of the individual George Orwell to the property author. So this was pretty easy. Now, again, let's have a look at loose binding and strict binding. So first here we have a strict binding relationship. Strict binding, again, we are restricting the range of a property to a specific class. And moreover, we are saying that all members that we are talking about in that class definition, they must comply to that binding. So the binding is strict. So first, let's have a look at the description logic expression in gray. So here we say poetry is everything which has been authored by a poet. So all poetry must be authored by a poet and by nothing else. So it means if the author writes poetry, he's a poet and nothing else. So we define poetry as being a class, and then we simply translate the rest of the description logic expression here, and we say, okay, so this class poetry is an RDFS subclass of something which is more complex, so therefore we again write it as a blank note embraced in square braces, and then we define again a restriction on the property author. So we define this is now an OWL restriction on OWL on property author, and we say here that all values in the range of author must be from the class poet. So OWL, all values from, and then the class poet. So this is a strict binding with this universal quantification on the range of a property. Strict binding. Okay, another example now for loose binding. So again, let's first have a look at the description logic expression. We see here in gray, we say a reader is somebody who reads books. Possibly you also read somebody else, but a reader should be a subclass of everybody who is reading, besides other things, books. So therefore it's a loose binding, it's not a strict binding. So again, look at the definition for OWL. So first we define reader as being an OWL class, and we say this OWL class is a subclass of a complex expression, which again here is expressed with the help of a blank note. So therefore we have again square braces surrounding the restriction, and we define now in the square braces our restriction on this class definition, and we say this is an OWL restriction on a specific property. The property here is now reads, and we say according to the range of that property, the restriction should hold for some values of the type book. So this is a loose binding that some values of the property reads must stick to the value of the class book. That's a loose binding. So strict binding, loose binding, and restriction to a constant. These are three possibilities how you can define complex classes in OWL by restricting the range of a property or the value of a property. At last, let's have a look at cardinality restrictions. So you have already learned about that example of the string quartet, and in the same way we can also, for example, define a class of books which always occur with 4 volumes, which are then called a so-called tetralogy. And a tetralogy, if you look here, for example, first at the description logic expression, a tetralogy is a subclass of anything which has exactly 4 volumes. So here, in front of the property, in braces, I write the number restriction. And if I want to restrict this to an exact number, I write it with an equivalent. So equals 4, means exactly 4. And I also can write upper and lower limits, upper and lower bounds with greater or equal of than, or with a smaller or equal than. So let's stick to the example here with the tetralogy. So I define tetralogy as a class, and this is a subclass of a complex expression, again surrounded by square braces. And I define that here again as a restriction. So in the square braces we have an OWL restriction on the property has volumes. And I say here exactly the cardinality of the class members here, of the things that are here in the class considered, they must have exactly 4 volumes. So it means a tetralogy is something which has 4 volumes. It's nothing which has only 3 volumes. It's also nothing which has 5 volumes. It's something which has exactly 4 volumes. And then with has volumes, usually the single volumes, number 1, number 2, number 3, and number 4 should be expressed then here as individuals. So this is then the cardinality restriction to an exact number. And if you combine this with min cardinality or max cardinality, you would restrict it to upper or lower bounds, likewise. And you will see plenty of examples of that then in the exercises to these lectures. So these were already some restrictions to complex classes in OWL. In the next part of the lecture, we will see how you can also define restrictions on properties and define property hierarchies or special properties.